Good morning to those of you on the West Coast. Good afternoon to those of you joining us from the East Coast. And good evening to anyone joining us from Europe or Africa or stations further east. Welcome back to those of you who I've met before. And for those new guys, welcome. And thank you for joining this, the 32nd of our regular series of short courses on pumping topics. This one will last about 35 minutes, allowing us the time for a Q&A session after the presentation. Now, as those of you who've attended previous sessions will know, we're deliberately steering away from product presentations and towards educational content, addressing a different pumping topic in each one. This, of course, is very important these days in the new world order of many engineers working from home, which makes in-workplace training that much more difficult. I do include a few slides at the end of the presentation to remind you of who we are and what we do, but I don't dwell on them, and they will be in the PDF copy of the presentation that you get after this presentation, so you can peruse them at your leisure. So let me see if I can restart the screen share properly this time, because this morning I messed it up. And there we go. Let's check it. There we go. It's working properly this time. This morning I messed it up, and all my customers this morning were seeing my internal screen rather than the proper presentation. But this time I think I've got it right. So if you can't see me or can't hear me properly, then put something in the chat, please. Nobody told me this morning. We went through the whole presentation with the wrong screen up. Anyway, here is a listing of the previous short courses we've run during the last 3 years. If you've missed any of them, you can get a copy of the materials from our website, ruhrpumpen.com, and follow the link to RP Short Courses. If you go to ruhrpumpen.com, you get to this screen, and here is the link to RP Short Courses. If you click on that, it takes you to this screen, and you'll see all the recent courses listed, and you can click on any of them to see the course material. Only the most recent of the previous 30 courses are up there. The earlier ones, which I've improved and repeated later on, aren't there. So this seminar is going to look at pump instrumentation, with a particular emphasis on vibration monitoring, and with a section helping you to understand what the readings you obtain tell you about your pump installation. We'll hold a Q&A session at the end. It will not be a fully interactive Q&A. It's impossible with as many attendees as we've got today. I think I had 290 registrations for today's session, this afternoon's session, that is. And certainly we've had 200 attendees for all of the previous sessions. So it won't be fully interactive, but we'll do the best we can. Please use the Q&A facility at the bottom of the screen to ask any questions or make any comments. I'm not an instrumentation expert, and I expect there are some instrumentation experts who might have some valuable suggestions to put into the Q&A. So please do. I really appreciate it. All the questions and answers, well, I'll try and address those that I can live at the end of the session. The rest we'll address by mail in the coming days. We're recording this session and we'll make it available to you all as a YouTube link, as well as by emailing you a PDF version of the slideshow and the Q&A summary from both of today's sessions. So, why is your pump vibrating, and is it serious? This is what we'll look at today. Well, there are two general physical causes of vibration. It's either a mechanical cause, such as balancing, misalignment, bearing problems, or hydraulic causes, such as liquid turbulence, cavitation, or low-flow suction and discharge recirculation. And there are three methods of measuring the vibration. Velometers, which measure the velocity of the vibration levels in inches per second or millimeters per second. And we have accelerometers, which measure the rate of change of velocity over time. And the units of acceleration is inches per second squared or millimeters per second squared. Now, these first two are used on pumps which have ball bearings, anti-friction bearings. If you've got sleeve bearings or hydrodynamic bearings, then we use displacement vibration proximity probes. These, as you'd expect, measure the displacement or the slight movement of a rotating component, which is usually the shaft, and it's measured in mils, thousandths of an inch, peak to peak, or in microns, again, peak to peak. Now, many vibration devices can measure either in root mean square or peak to peak. Most commonly, the readings are given in RMS, with the peak to peak values used for detailed analysis. RMS is root mean square, which means you square all the individual peak to peak values, calculate the mean by averaging them, and then you calculate the square root of that total. So in this example, you've got 3 peaks here. You square them. You take an average of those 3 peaks, and then take that average reading and take the square root of it. And that gives you the root mean square. So the root mean square of these 3 figures is 0.118 mils. When we're measuring vibration, we measure it in 3 planes: horizontally, vertically, and axially. Now, for pumps with anti-friction or ball bearings, this shows where you measure and how you measure. Here we see it: horizontal plane, vertical plane, and axial plane. There'll be a dimple on each bearing housing showing where these readings are supposed to be taken. And it may be done with a handheld meter like this. And so you've got a probe that will locate in those dimples. Or you might have a permanently installed accelerometer or velometer. This slide shows simplistically how an accelerometer works. Vibrations from the pump housing, the bearing housing, cause the mass inside the accelerometer, there and there. It causes it to squeeze the piezoelectric material here and here. And this produces an electrical charge proportional to the force exerted, proportional to the vibration. This is an accelerometer. Now, a velometer, the construction is very similar to an accelerometer, but they contain integration circuitry, which converts the acceleration values to velocity. Now, as API 610 specifies vibration limits in velocity units, it makes a lot of sense to have a velometer. Here are the vibration limits of API 610 for anti-friction bearings, for ball bearings. It's table 8 in API 610. And what it says is that the vibration at any flow rate within the pump's preferred operating region, and let's remember that the preferred operating region is from 70% to 120% of best efficiency point flow. Okay, 70 to 120% of best efficiency flow. So within that preferred operating region, the maximum vibration level shall be 3 millimeters per second, root mean square, which is 12 mils, root mean square. Outside that region of 70 to 120%, so the allowable increase in vibration that flows outside the preferred operating region, but within the allowable operating region. So that really means from minimum continuous flow to 70% of best efficiency point flow. It says the allowable increase in vibration is 30%. So within the preferred operating range, the limit is 3 millimeters per second, or 12 mils, or outside of it, 30% more, which is 3.9 millimeters per second, or 0.16 mils. When you have sleeve bearings, then you use displacement proximity probes. These measure the gap between the shaft and the bearing sleeve. More specifically, and a little more verbose, the displacement proximity probes are powered by a proximeter, which provides an alternating high-frequency voltage from a minus 24-volt DC supply to the coils within the proximity probes. This causes an electromagnetic field at the probe tip here, the effect of which is to induce alternating eddy currents in the shaft. These eddy currents then generate a magnetic field emanating from the shaft, which opposes the field from the probe. Then as the gap between the probe and the shaft varies, for example, if you've got a bent shaft, so this gap will open and close as the shaft goes round, then the probe electronics measure the field changes and they generate an output voltage proportional to the change in the gap. So they accurately measure the radial movement of the shaft in mils or in microns. If you have ball type, if you have sleeve radial bearings and ball thrust bearings on a pump, which is quite common, then you'll have accelerometers or velometers on the thrust bearing to measure their vibration, and you'll have the proximity probes in the X and Y directions to measure the radial deflections. But if you have tilting pad thrust bearings, then you will have X and Y probes and an additional one, a Z probe, measuring in the Z direction. So you'll have an X probe, a Y probe, and a Z probe acting on the end of the shaft there. Here are the vibration limits for sleeve and tilting pad bearings, hydrodynamic bearings. And here is the key for this formula that's in here. So AU is the amplitude of the measured overall displacement. And here is the formula for it in microns, peak to peak. And here is the formula for it in mils, peak to peak. And it's not to exceed 50 microns peak to peak or 2 mils peak to peak. That's again within the preferred operating region. Outside the preferred operating region, you have a 30% uplift on that. Now, as well as the XYZ proximeters, you will often use, well, you will always have a key phaser proximeter, which is aimed at the keyway. This will identify where the shaft displacement that you've just established via the X and Y probes, it'll establish where it is occurring, reference to this keyway. For example, it might say 20 degrees clockwise from the keyway, and that you know the plane of the out of shapeness of the shaft. The key phaser is also useful for measuring the speed of the shaft as a tachometer. Very useful if you've got a variable speed pump. Now moving on to troubleshooting. You're getting an elevated vibration reading. Well, the first thing to consider is the high vibration reading associated with a sudden power increase or decrease? Well, the next two slides illustrate 11 possible causes of vibration, 7 of them associated with a power increase and 4 with a decrease. This is your first step in understanding pump vibration and working out what might be wrong with your pump. Many clues can be obtained by checking all the normal pump parameters, such as sudden power variations. So first, a power increase, sudden power increase. First thing to look at would be if piping loads are excessive. That could cause wearing contact. Impeller wearing is touching the case wearing, damaging friction, higher power. Another possibility to consider, extreme wearing wear. This can double the clearances, which would allow greater internal recirculation, reducing the efficiency, so you get an increase in power. You should look at the system resistance, such as maybe a bypass valve is faulty and fixed open. So you've got pump discharge flow increases, and if your pump flow increases, the power would increase. So check your system resistance curve. Number 4 would be to check your anti-friction bearings and check the oil level, oil quality, and oil grade is correct. Oil level's a very important one. Funnily enough, too much oil is worse than too little oil and will cause you bigger problems. Sounds counterintuitive, but too much is worse than too little. Number 5, if you've got an oil mist lubrication system, verify that it's operating correctly. If you've got damaged bearings, that would lead to high power. Another possibility is you've got mechanical seal problems. Prior to seal leakage, you've not got a leaking seal yet, but you've got damaged faces, perhaps. So check that the seal faces are clean and not eroded due to liquid crystallization. For example, if you're pumping sodium hydroxide, it forms crystals if it comes into contact with the air, and those crystals can shred your seal faces. And that's why you normally have a plan 62 quench on a sodium hydroxide pump. Similarly, on a hot oil pump, you can get coking of the seal faces when the liquid comes into contact with the air, and though again those coke particles will shred your seal faces. So that's why you have a steam quench on a hot oil pump, for example. So those are obvious things to check. And the final one, as a quick preliminary checklist, would be your bearing oil temperature. Hotter the oil, lower the viscosity. And if it gets down to 11 centistokes or lower, then it could cause the bearings to start skidding against the inner and outer races. Bearing damage, bearing vibrations again. Now, if you have a sudden power decrease combined with high vibrations, then we've got 4 things to consider. First of all, as an initial thinning down exercise, cavitation might be the cause. Well, this would cause the pump flow and head to reduce, and hence the power would reduce. You'll also get the characteristic sound of cavitation, which sounds like someone's taken a handful of gravel and thrown it in your pump. Next possibility, consider if you've got an inline suction filter. Maybe you're not monitoring it properly and it could be blocked due to solid particles. This would be particularly so on a newish installation where there's still a lot of dirt in the system. If the filter's blocked, the pressure drop across the filter can cause cavitation, and it'll certainly cause lower flow in either case. So lower flow, lower head, lower power. Another possibility, if your system resistance curve has gone up due to a system upset condition, it means that the flow would be lower. So the pump power would decrease. And the fourth and final one of this preliminary survey would be if the pump has a minimum flow bypass line and an ARC valve, an automatic bypass valve, to ensure that the pump doesn't ever flow below its minimum continuous flow, maybe it's jammed closed. And this would cause the pump to run at too low a flow rate and result in the power being very low. So there's 4 initial possibilities to look at. Well, having eliminated the obvious, we can then look in more detail and refine our investigation with a more detailed spectral analysis. Detailed spectral analysis is a specialist field. I'm not qualified to lecture on this, and it's well beyond the scope of a 30-minute short course. But this is the kind of analysis that a vibration specialist can offer you. But what I can offer to you in the next 8 slides is vibration analysis for dummies, a crib sheet to give you a clue as to what might be happening in your pump. So looking at the first slide, vibration frequencies of 0 to 40% of running speed. Well, 10% of the time, seal face is rubbing. They're dry, no film. 20% of the time, anti-friction radial bearing damage. 90% of the time, it's thrust bearing damage. But this is the interesting one, 40% of the time, casing mounting bolts to base plate are loose. Well, that gives you a real clue as to things to check. This is very quick and easy and should be checked before you take the pump out of service. You'd have to take it out of service to check radial bearings and thrust bearings, for example. So first of all, check the obvious, check the simple things. Second slide, frequency of 40 to 50% of running speed. And it's a similar story here. I'm not going to go through every slide in detail. There's 8 of them here. I'll just leave this one up on the screen for 30 seconds or so to let you get the picture of it. You might like to print out these slides and keep them in your bottom drawer as a quick reference if you ever need to speak to a shaky engineer. Third slide, frequency of 50 to 100%. And this one is quite interesting in the fourth slide, peaks at running speed. 90% of the time, it's a major rotating component unbalanced. But 40% of the time, it's misalignment. Now, this requires taking the pump out of service. This can be checked without taking the pump out of service. So that's the first thing to check before you take the pump back to the workshop to have a look at it. It's the easy thing to check. Frequency is of 1.5 times running frequency. Frequency of 2 times running frequency. 50% of the time it's misalignment, and 50% of the time it's excessive forces. So 2 things that can be checked without taking the pump out of service. Vane passing frequency, the frequency at which the impeller vanes pass the volute lips or cutwaters. 90% of the time that's the cause. Now, this is a possible design issue on a new installation, but it's not a maintenance issue. It's not something that will change over time. This is something that would be on the installation from the start. As you say, it usually occurs if you've got a maximum impeller diameter, which is rare. And finally, very high frequency, but with high frequencies and the peaks varying frequently, 90% of the time, that's cavitation. And again, you'll have the acoustic sound. You'll hear the sound of gravel in your pump, effectively. So what does API 610 require? Well, API 610 references API 670, which covers selection, installation, and best practices for these: accelerometers, proximity probes, RTDs, thermocouples, key phaser proximity probes, and magnetic speed sensors. So these are what it covers. I'll leave this on screen for a few seconds to let you read it in peace. So API pump suppliers will be complying with API 670 for these items. Okay, we've looked at vibration. Now we're going to look at temperature. For anti-friction bearings, the RTD will be spring mounted so that it rests gently against the outer race, here in green, the outer race of the ball bearing. So there, resting against that. For tilting pad bearings, the RTD will be installed in usually two of the tilting pads. And for journal bearings, sleeve bearings, again, it's embedded in the metal of the bearing. Usually this type spring-loaded and with a spring clip there to hold it in place. Now a few slides to show how instrumentation is typically installed in various pump types. Here's an OH1 or OH2 pump, one accelerometer, and one bearing RTD. Wired to a J-box, and in this instance, the wiring is run in conduit. Now, some customers prefer to see vibration and temperature signals run separately to separate J-boxes, or certainly to have a segregated J-box, so that you don't mix millivolt and milliamp signals. So this is a most common instrumentation on an OH1 or OH2 pump. Less typically, we see occasionally 3 accelerometers. Here we go, one there, one there, one there, measuring in the X, Y, and Z directions. Here you'll see the Z direction is being measured on the pump cover or back plate. It can usually, and is more commonly, measured on the end of the bearing housing down here. In this instance, we have a fan-cooled bearing housing, which makes locating it a little more tricky. But there is usually a Z probe location here at the bottom of the bearing housing, even on a fan-cooled bearing. What else do we see here? We see 2 RTDs, one on the radial bearing here, and one on the thrust bearing here. Here's a typical between bearings pump with ball type bearings. So we see an accelerometer on each bearing and an RTD on each bearing. Again, wired in conduit. There should be a J box somewhere over here. We can't see it. There's a pump in the way. And here's a bigger pump with hydrodynamic bearings. So we have an X probe, a Y probe, a Z probe. We have some RTDs, and on this one, apparently we have a key phaser in the end of the shaft on the non-drive end, which is unusual. It's more commonly on the drive end. We'll see that in a next slide. So this is another example of a pump with sleeve and tilting pad type bearings. So we see the radial probes, X and Y, here and here on the other side of the pump. We can see the key phaser here being angled down and shooting at the keyway here. And we see the radial RTDs, radial bearing RTDs here. Here is the non-drive end of the same pump, and we can see 2 axial vibration probes here acting on the end of the shaft. And here we see the axial RTDs measuring the temperature of the tilting pads. Again, we see the radial vibration probes here, another one on the other side. Now this is the thrust pot on a vertical pump, a VS1 or VS6 pump. Now, European and Asian motors generally don't take thrust loads, so in those cases we use a separate thrust pot. American motors are designed to take thrust loads, so you don't need a separate thrust pot usually. But if you do have a thrust pot, here's where you'd measure the RTD and your accelerometer. Let's look a bit at cable management. Now, on a simple pump, an OH1 or OH2, instruments are frequently very close to skid edge, so no cable runs and J-boxes are necessarily required. However, they are commonly specified, and because they're commonly specified, we often have to supply them. Now, of course, on more complicated pumps, between bearings pumps, especially those with sleeve and tilting pad bearings, you've got a lot of instrumentation, so of course it must be cabled to one or more J-boxes at the skid edge. Cables are commonly run either in conduit or cable trays, and the decision on which it is really depends on geographical location. In North America, conduit is most commonly used. In Europe, cable trays are used. In Africa and the Middle East and India, it can vary. So here are cable trays, commonly used in Europe, and here's conduit, commonly used in the United States. So here is a pump set with cable trays. Very neat. And here we see one with cable trays. It's an OH2 pump with only one instrument. It's an RTD. Now, in this case, clearly there was a requirement that we cable it to a J-box at the skid edge. So this is what you end up with. Now, I would question if it was truly necessary. To my mind, it's as easy to wire to this point here and on the RTD, the instrument itself, as it is to wire to a J-box. But there you go. You pays your money and you takes your chances. And here we see a pump that is run with wiring in conduit. Local push button stations. We don't often supply these, but some customers ask us to supply local push button stations. I've seen it particularly in Indian-based specifications. There is no standard design, so that you really need to spec up exactly properly what it is you want them to do. As I understand it, the intent generally is to have something nearby the remotely controlled pump to give visual contact on the equipment before starting it and to instantly shut it down in an emergency. So that's what can be supplied if you want it. More commonly, there is just a stop button, an emergency stop button close by the pump. That's a requirement of code, I think, and that will be supplied normally by the installation contractor, not by the pump suppliers. There's no reason for us to supply a stop button. Machinery monitoring systems. These are usually installed in the remote control room, and it takes the signals from the accelerometers, the proximity probes, the RTDs, and the speed sensors, and it processes them to give analytical reports for trending, scheduling maintenance, and predicting failures. Most commonly, they're supplied by Bentley Nevada and Metrics. They're the two main names that we come across all the time. There are, of course, others out there. But these can be supplied by the pump vendor, but more commonly they're supplied by the EPC. Sometimes the pump supplier supplies the racks for installation in the cabinets, and the cabinets are supplied by the EPC. And the reason for this would be, well, the chances are that you'll have several pumps from several suppliers all going into the same cabinets. The crucial thing here is to clearly specify what you want. Don't just ask the pump vendor to supply a suitable MMS. You don't know what you'll be getting, and you'd be very hard to compare like with like. So this is the simplest low-cost system. You have one common cabinet and one common rack for all the pumps. The intermediate system here, one common cabinet with one rack for each pump. This is probably the most commonly specified way to ask a pump supplier to supply them. We just supply one rack for each pump, and the EPC supplies the common cabinet. And this is the most expensive system, where you have one cabinet for each pump and one rack for each pump. This is usually required when pumps are installed in separate locations or separate pumping stations and with separate control rooms. You also need to tell us whether temperature monitoring is to be incorporated in the MMS. Sometimes it is, sometimes not. It's quite common to have only the vibration signals in the MMS. The temperature signals are routed to the PLC or DCS. Likewise, do you need a touchscreen display? The human machine interface, HMI. Frequently, the operation is directly via the SCADA system, and the customer doesn't need a local display. But sometimes they do. It's expensive kit. And now finally for today, smart pump monitors. These are being pushed by many pump manufacturers these days. This one in the slide is the KSB Guard. Flowserve has LoRaWAN. Sulzer has Sense. So what are they? What do they do? They have a sensor unit attached to the pump, recording the temperature and the vibration data from the bearing housing, goes to a transmitter, which sends it to the cloud, where it is picked up by the pump manufacturer, KSB in this instance, and they will analyze the results and give you an alert if they think you need to do some maintenance. This is mainly of use for industrial users who don't have resident engineers. Refineries and production facilities tend to have specialist engineers who look at vibrations and condition monitoring of pumps, and so they're not needed. But I would be interested to hear of your experiences in using this kind of service. Does it work well? Let me know. We've got a Q&A session there if somebody has some feedback on that. Well, that pretty much concludes the fun for today, apart from the Q&A, of course. I just get to advertise the next of the short courses. That's going to be on handling viscous fluids and separately on handling slurries. It will look at how to correct standard water performance curves for handling viscous fluids, as well as the considerations to be taken into account in selecting and specifying them. And then I'll do the same thing for handling slurries. Now, those of you who use pump manufacturers' curve drawing programs, it automatically does calculate these corrections for you. But the point is, you need to understand what is happening behind the curve drawing program. You need to know what happens if a pump that you're designed for running with hot oil, for example, at 10 centistokes, what happens when it's running at 50 centistokes or 100 centistokes? What will happen to the performance curve? And that's what I will show you in the next session, which is on Thursday, the 9th of May, as usual, 2 sessions, one at 8 o'clock in the morning and one at 5 o'clock in the afternoon, my time. That's for you guys in the Americas. And then for the future, I've got a few more ideas, but maybe you have suggestions. What would you like me to cover? So if you can give me some ideas, I'll be happy to consider them. smith@ruhrpumpen.com. I'm leaving this meeting open for a little while to allow you to post in the Q&A box, and I'll endeavour to answer those that I can here and now. Those that need a fuller answer, I'll answer within the next few days. And anything you think of later, drop an email to marketing@ruhrpumpen.com or directly to me, smith@ruhrpumpen.com. The marketing team are standing by and they'll direct your questions to the best person to answer them. And they are the guys that will be sending you the YouTube recording and a PDF of the presentation. If you need a certificate of completion, again, send an email to marketing@ruhrpumpen.com. And here, as usual, right at the end, 8 slides about Ruhrpumpen to remind you of who we are and what we do. They will be in the PDF copy of the presentation you get, so you can peruse them at your leisure, and we won't spend any time on it now. So that just leads us now to the Q&A. So let me stop the screen share and let's have a look and see what we have in terms of Q&A. Anonymous attendee is asking if we can quickly show slide 2.2. Let's get back onto that then. Share screen, the presentation. I'll just leave that on the screen for the moment, and so that our anonymous attendee can have a look at it at his leisure. And I will now move on to the next question, which is from Shrikar Hathwar, who says, can thermocouples be used in all places where RTDs are used? Is there any limitation for use for thermocouples and RTDs? We see RTD requirement in pumps more often than thermocouples. Why? I will ask our instrumentation engineer for a definitive answer on this. We certainly do see RTDs more commonly than that. And I think possibly it's because I think possibly that thermocouples tend to be for higher temperatures and RTDs more for the temperatures in the ranges that we're likely to see in bearings, in bearings in pumps. Well, the anonymous attendee has said, when is Ruhrpumpen planning to launch its own condition monitoring kit, like Sulzer's Blue Box? Well, it rather depends what you guys say. Do you want them? I haven't, I'd be very interested to hear from people who made use of KSB or Flowserve or Sulzer's boxes. Are they any good? Does the system work? Would it be advantageous for us to do them? We'll take it into consideration. Shrikar Hathwar says, in some pumps, like for example an OH2 pump, we have both radial and thrust bearings very close to each other in a common bearing housing. In such case, does it make sense for the customer to ask for an RTD or accelerometer for each of the radial and thrust bearing instead of a common instrument for both bearings, just because they're in the same bearing housing located so close to each other? Will offering separate instruments help the customer in any way than a common instrument? Yes, I agree with you 100%, Shrikar. They are normally so close together that it doesn't matter. We would most commonly supply one RTD and one accelerometer, but sometimes the specification might be for more, in which case that's what we have to do. But yes, you're right. Normally, you can't tell the difference. Shrikar Hathwar says, in a local control station, do we have only start, stop, push button, or will there be other instruments and parts also? I remember some customers asking for local control station with ammeter. What does it do in that? Most commonly, the pump vendors do not get involved in these local push button stations. It's most commonly done by the installation contractor. It's part of the on-site wiring. Every time I've seen them specified, nobody quite knows what they want. And all through the phases of supplying the pumps, questions start going back, oh, no, that's not what we meant. Well, you didn't tell us what you meant. What do you want? And nobody really knows. That's why we prefer to keep out of that side. Shrikar Hathwar says, can an instrument be directly connected to the MMS or DCS without a J-box mounted in the pump skid? If yes, what difference it makes than the ones connected via a JB in between? Why different customers need different ways in this context? I will defer answering that. I want to get some more information, perhaps from my instrument engineer expert on that. I'm just going to stop this screen share. Okay. Andres Loggia says, thank you very much for this session. Well, thank you for attending. It's my pleasure. Woodrow Lorenz says, does Ruhrpumpen ever provide lateral and torsional natural frequencies for pump units? These frequencies can be helpful in troubleshooting vibration issues. I've seen these values determined analytical, FEA model, or by shop testing. You need the entire drivetrain, e.g. motor, coupling and pump shaft, in order to properly determine these frequencies. Yes, we absolutely do it, especially on more complicated, larger, high-speed pumps in particular. An OH2 pump doesn't normally need lateral and torsional analysis, but a high-speed axially split case pump or barrel pump, yeah, we will normally have to do these calculations. Vertical pumps, torsional vibration analysis, natural resonant frequency analysis, very important. So yes, we do regularly do those on more complex pumping systems. Orlando Uriola says, RTD signals are commonly sent to the MMS or to the DCS? Question. What is preferable option? Not for us to say, it's for whatever the end user or the installation contractor is wanting. How is he setting up his system? John Patinrin says, can we get the training material, the PDF, beside the recorded video after? Yes, you'll get both. You'll get a link to this video. You'll also get a PDF version of the slideshow. Ali Badu says, hello, thank you for your presentation. You're welcome. I would like to know if these pumps are available in North Africa, like Morocco. Absolutely, yes. Yeah, we're a worldwide company and we can supply them worldwide. We have sales offices across Africa. Anonymous attendee says, when is the next webinar and topic? Well, it's on the 9th of May, and it will be on viscous corrections for pump curves and slurry and handling and adjusting slurry curves as well. That's the planned next one, 9th of May. And anonymous attendee again, hello, thanks for the presentation. According to your experience for centrifugal pump installed on the metallic platform, is it necessary to install the vibration pad per API 686, recommended practice for machinery installation and installation design, or not applicable for centrifugal pumps? On the metallic platform, I'm not quite sure what you mean about on the metallic platform, whether you mean on an offshore drilling rig or production platform. I'm not immediately able to answer that question. You might like to rephrase it so I can better understand it. Let me look and see if there are any more questions. Yes, there's a few more here. Yeah. In past years, we usually see customers asking MMS instruments suitable for Bentley Nevada Rack 3500 or something similar to that. Nowadays, we often see customers asking for instruments to be suitable for Orbit 60 systems. What's the difference between Bentley Nevada 3500 and recent Orbit 60? I'm not an expert in that field. I will ask my instrumentation engineer for an answer to this question, and I'll get it to you in the written Q&A. Heather Leach says, thanks for the presentation. Are key phaser proximity probes normally required for locating vibration issues? Does this help troubleshooting pump vibration issues? Yes, the X and Y probes will tell you that the extent of the bending of the shaft, but not in which plane it is bending. With the key phaser, it tells you that it would be, say, 20 degrees clockwise of the keyway. It tells you in which plane it is bent. Helps with the troubleshooting. Hans Bert says, answer to one of your first Q&A questions, RTDs are more accurate compared to thermocouples, but have a limited range. Thermocouples can handle higher temperature ranges and react faster. Thermocouples are typically used for example, in mag drive temperature monitoring. For bearing temperatures, speed is not that critical. Hence, RTD most of the time is sufficient if the temperatures are not elevated. Thank you, Hans. That confirms what I said in a lot more detail. So thank you very much for that. Okay, that appears to be all of the Q&A. 20 questions there, so thank you very much. So that just remains then for me to say thank you for attending today. I enjoyed preparing it and presenting it. I hope you found it useful. We will send through all the materials to you shortly, including the Q&A. Couldn't answer all the questions. I'm not an instruments expert. I will get answers to those questions I couldn't answer and get them back to you guys as soon as I can. It'll be early next week, probably before it all happens. So nearly 6 o'clock here, which makes it beer o'clock. So thank you for attending today. See you on the 9th of May in 4 weeks' time for the next short course. Bye-bye.